So last time we talked about the use of maximum likelihood and parsimony as means of estimating phylogeny. These being two different criteria to determine what the best tree is, how to compare trees and to figure out which one is the best hypothesis for the data that you have at hand. My goal today is to talk about another major technique that is very popular called Bayesian phylogenetics, the use of Bayesian point of view and statistics to estimate phylogeny, and also to cover a couple of measures of confidence that we have in the results that we find from our analyses. Unfortunately, I want to begin by noting the passing of one of the people that I consider to be one of the prominent systematists in the world, Chris Thompson, who worked at the Systematic Entomology Laboratory at USDA in Washington, housed in the Smithsonian Institution, passed on Friday. Chris was an expert on flower flies or hoverflies, the family Syrphidae. One of the anecdotes that people were posting over the weekend was that Chris, who working for the USDA, would tell the mucky mucks who came to inspect the lab that he worked on flower flies. And of course, we know that the flower that he was talking about is spelled Flower, but the agriculture bigwigs always thought that it was spelled Flour, and therefore that the work that Chris was doing had direct economic significance. He did not disavow them of that or disabuse them of that notion. Chris was outgoing, garrulous. Some people found him grating a bit at times. He was a man of strong opinions, but very generous, both his time and all of his resources of any shape. And I have certainly missed him the past few years that he has not gone to after he retired, he stopped coming to the meetings of the Entomological Collections Network, which he helped to found, was critical in founding, and the Entomological Society of America, where he served as an officer for many years. He also served as commissioner in the International Commission of Zoological Nomenclature, the governing body for the names we use for animals in the world. I think he was a brilliant guy. Always much more forward-looking than even many of his younger counterparts. I'm certainly going to miss him a lot. So let's start out today. I'm going to talk about Bayesian statistics. I don't know how much you guys were taught the perspective of Bayesian statistics in your undergrad or even in your grad days, but it's certainly something that's become very popular these days, and you find it ubiquitously through all fields that engage any sorts of numerical analyses at all. But I want to step back, and before we talk about Bayesian statistics, just briefly review what people call the frequentist, or the more classical approach to statistics. In fact, Bayesian statistics is older, so the fact that we call the previously normal statistics classical is kind of an anachronism. But I'm sure you're all familiar with this. I'm sure this is taught in the nature of science course that the department offers. But typically, when you are examining a question, you start out with a hypothesis of what you think is going on in a particular situation. And so actually you have a hypothesis of what you think is going on, but then you always have a null hypothesis, which is basically the idea that nothing's going on, that any differences you observe are due to chance. And so this approach to the experiment or the field test involves a comparison of the alternative hypothesis against the null hypothesis. So you start out with your hypothesis, you gather data, and then you construct, you design the experiment such that the data you gather is appropriate for a particular test statistic. So you're going to take your data and derive from that a test statistic. And that test statistic, let's see how many times I can say it without stumbling, is something for which you know the frequency distribution, or what the statisticians call the probability density function of that test statistic. Missed that one. For example, here we have a graph of the probability density function for the chi-squared statistic. You're all familiar with chi-square. The different lines here, the K refers to the number of degrees of freedom in your experiment. So the yellow, here's the graph of the probability density function for chi-square with 1 degree of freedom. And this is the value of chi-square here, and this is the frequency. And so the area under this curve is going to equal 100%. So typically, the scenario is that you gather your data, you calculate your test statistic, be it chi-squared, a t statistic, any of these things, and then you ask the question is, what is the probability of coming up with a statistic of this particular value if the null hypothesis is true? So I come up with a value of chi-squared of 4.2 with, pick a number, 3 degrees of freedom. And then I want to ask, what is the probability if the null hypothesis is true? That is, that all differences are due to random. There's no underlying mechanism there. What is the probability of observing that value of chi-square or greater? And if the probability of observing that is so small that it exceeds your gut threshold, what people typically call an alpha value. So if the probability is less than an alpha value of, say, 5% or 1%, those are the two common values, then typically you would say, okay, that's low enough that I do not believe that I would have gotten this result if the null hypothesis were true. Therefore, I reject the null hypothesis. And my alternative hypothesis becomes my current best guess. So basically, you're saying, what is the probability of observing these data given the hypothesis, the null hypothesis? So Bayesian statistics turns this entirely on its head. And so it may take a little bit for you a little bit of work for you to get your head around it. It certainly has taken me some work to get my head around it, and that's why I entitled this slide "Through the Looking Glass," because everything is looking kind of backwards. If you don't know, "Through the Looking Glass" is a reference to Lewis Carroll's Alice in Wonderland book. So let's approach this by taking an example that would be very, very familiar to you. So let's say I have 2 cubical dice, the time with a number on each of the 6 faces, and I'm going to shake them up and roll them out. And the question is, what is the probability of rolling snake eyes? And if you don't know this, I've discovered people don't know what snake eyes are. Snake eyes is a value of 2, so 2 single pips coming up when I roll the dice. So basically, there's only one way to get a 2 when you roll 2 6-sided dice, and that is that a 1 comes up on both of the dice. So basically, this is a joint probability. So what is the probability of getting both a 1 on the first die and a 1 on the second die? So this is what I'm representing here with this notation, where PR stands for the probability. And in this case, since it's a joint probability, I'm asking, what is the probability of A and B occurring? The intersection of those two events, if you prefer to think about it that way. It is probably intuitively obvious to you but we have to stipulate this, that the probability of A and B occurring is equal to the probability of B and A occurring. Makes sense, right? Nothing but particular spectacular there, but it's going to become important here in a second. So I want to now express that joint probability, the probability of A and B occurring, as a conditional probability. So let's take 1/2 of those two that I said were the same, the probability of A and B occurring, or the probability of B and A occurring. The probability of A and B occurring is equal to the probability of A occurring, that is, on the first die that I roll, I get a 1, times the probability of B occurring given that A has occurred. That's what that vertical bar means there. Since these are two independent events, this probability is no different than the probability of B. But in other situations where the events are not independent, this is critical. So to translate this into English, the probability of both A and B occurring is equal to the probability of A times the probability of B if A has already occurred. Since I started out by saying this is basically commutative, that it doesn't matter which order you present these things, you do these things, the joint probability is the same, then the probability of A and B occurring equals the probability of B and A occurring. Putting in my conditional form of the probabilities, this should say only probability of A. No, that's right, probability A and B. So yeah, A and B. So that's probability A times the probability of B given A. Then, just substituting on both sides here, the probability of A times the probability of B given A is equal to the probability of B times the probability of A given B. So I'm just reflecting these two things. If you divide by the probability of A, then we have what's known as Bayes' theorem, very famous theorem, in which it states the probability of B given A is equal to the probability of B times the probability of A given B divided by the probability of A. Now, since A and B here are kind of amorphous concepts here, let's make this a little bit more concrete. If B is your hypothesis and A is the data that you observe, then to restate Bayes' theorem in this form, then the probability of the hypothesis that you have, given the data that you have, is equal to the probability of that hypothesis times the probability of observing the data given that hypothesis divided by the probability of the data. So some of this you're already familiar with. So one factor, the first one there that I list, I talked about last time, and that is the probability of the data given a particular hypothesis is what we were talking about was likelihood. So again, recognize that probability and likelihood are two separate things. But if I assume that a hypothesis is true, and then the question is, what is the probability of the data under that hypothesis? That is the likelihood. Now, the other components of this equation we haven't talked about yet, but you need to become familiar with. The probability of the hypothesis itself is what is referred to as the prior probability, or simply as the prior. And then the probability that your hypothesis is true, given the data that you observe, is what is known as the posterior probability. And it's the posterior that we're really after. We have a hypothesis. We want to know what's the probability of that hypothesis being correct. This is an example where the frequentist and the Bayesian approach to statistics are really opposite. The frequentist approaches the question from the point of view, what is the probability of seeing these data if given the hypothesis, given my null hypothesis? Whereas the Bayesian strives to get an answer to what is the probability of my hypothesis given the data. So how good is my hypothesis? A frequentist approach, you're basically eliminating hypotheses and ending up with the leftovers that are your best guess as to what's going on. Bayes turns that on its head. You may have noticed that that equation had one component in there that I haven't covered yet, and that is simply the probability of the data. So the probability of getting your data is the sum of the probabilities of the product of the probability of the hypothesis times the probability of the data given the hypothesis over all possible hypotheses. So as you can imagine, it's probably next to impossible in any interesting problem to know what all possible hypotheses are. And so the probability of the data itself is a value that is difficult to get your hands on. And so typically in these sorts of undertakings, we don't know what the probability of the data is. But if we take, since the probability of the data is going to be constant across all of these, that ends up meaning that the posterior probability is proportional to the prior probability times the likelihood. And those are two values that we can have a handle on and can calculate. So let's crystallize this maybe a little bit further and talk about an example. It's a bit of a contrived example that I lifted from somebody else, but let's try our hands with it to see how Bayesian inference works here. So let's say that we're interested in a particular parrot species, and there are two populations of these parrots. And these populations are identical. Well, I guess they don't have to be identical, but these two populations differ only in the frequency of eye color amongst individuals in those two populations. To give you some numbers, so we have eye color, population A and population B. We have three eye colors, blue, green, or red. What do I have here? I think I've got blue eyes, and well, I couldn't find it, green or red. I got yellow eyes there, but you get the point. In population A, 20% of the individuals have blue eyes, 30% have green eyes, and 50% have red eyes. And then in population B, 60% have blue eyes, 25% have green eyes, and 15% have red eyes. So our populations are differing in their eye color. And I think I guess I have to backtrack. It is important that this is the only thing they differ in, as you'll see the reason for that in just a second. So those are the two populations. Now, you're sitting in your office one day, and you get a package in the mail, and the package contains blood samples from this species of parrot. Unfortunately, the person who sent it to you didn't bother, or maybe they lost the labels that should have come with the package to tell you which of the two populations of parrots these samples came from. But although they didn't tell you which population they came from, they did give you a little bit of information, and that is that they gave you two pictures of the birds from which the sample came. So you've got a box of blood samples. They all came from one of those populations of parrots. We don't know which one, but we do have pictures of two of them from which the blood was taken. And both of them have blue eyes. So since you're interested, since your analysis is going to depend upon, well, I need to know which population it came from, we can ask the question, what's the probability that this box of samples came from parrots that belong to population B? That's our question. We know they both have, two individuals of those both have blue eyes. Okay, let me walk you through this because it looks more complicated than it really is. So up at the top, I basically have a restatement of the Bayes theorem, where the probability of the hypothesis given the data, that's our posterior probability that we want to calculate, is equal to the probability of the hypothesis, that's our prior, times the probability of the data given the hypothesis, divided by, this is the probability of the data, but since in this particular case, there are only two possible outcomes, it's either it came from population A or it came from population B, I can calculate the probability of the data. And so that is the sum over all possible hypotheses, in this case, under all possible samples that these samples could have come from, of the probability of that hypothesis times the probability of the data given that hypothesis. So to translate that a little bit, we're saying that what's the probability that this sample that had two blue-eyed parrots came from population B, so probability of population B given the observation of two blue-eyed parrots, is equal to the probability of population B times the probability of getting two blue-eyed parrots from population B divided by, so this is here the probability of the data that they came from population B, and this is the probability of data that came from population A. So if you recall back, the frequency of blue-eyed parrots in population A was 0.2. So the probability of taking pictures of two parrots at random from population A is simply the probability of getting one blue-eyed parrot in population A, 0.2, or I'm writing it out in fractions here, 1/5, times the probability of getting a parrot with blue eyes from population A, same value, 1/5 times 1/5, that equals 1/25. In population B, the frequency was 0.6 of blue-eyed parrots. So the probability of getting two blue-eyed parrots from population B, if this was done at random, would be 3/5 times 3/5, or 9/25. So now we have those values. Let's continue on. And we want to know what are the probabilities of the two hypotheses. That is, what is the prior probability? So one way to approach this, I mean, you could do it in a number of ways, but let's say you're totally naive. You don't know, you have no reason to suspect that these samples more likely came from population A than population B. You just got a package in the mail. Didn't say where it came from. There's only two possibilities. One reasonable approach to what the probabilities of what this sample came from is that it's 50-50. We don't know. Could have come from either one. There are two possibilities. So let's say that the probabilities that they came from a particular population are the same. So probability that they came from population A is equal to the probability that they came from population B equals 1/2, 0.5. I think now we have all the pieces of our puzzle, so let's go forward with the calculations. So according to Bayes' theorem, the probability of the hypothesis that they came from population B, given that we have two blue-eyed parrots, is equal to the prior that they came from population B, the hypothesis, 1/2, times 9/25 divided by, and here's the sum, here's the probability of the data in its form. This is population B, and this is population A here. If you do the math, I haven't done the math recently, I hope it works out. That comes out to 0.9. So Bayes' theorem is telling us that the probability that this sample came from population B, given that we know that two individuals selected at random from this sample had blue eyes, is 90%. So that's a heck of a lot bigger than what we started out with, where we said, well, naively, I don't know which population they came from. It could have been A, could have been B. The fact that you've got 2 blue-eyed parrots there means that the probability is 90% that they came from population B. So that tells you that the probability that this hypothesis is true, given the data, is 90%. And this is, just as a side note, just the opposite of what approach of what you would take with a classical statistics approach, where you're eliminating hypotheses. Now we're saying 90% probability that they came from population B. Another way to phrase this is that we started out with a totally naive expectation. We didn't know if they came from A or B. Could have been either one, equal probability. I have no reason to doubt that. I have no reason to think that they more likely came from one population than the next. But the data tell me something quite different. The data tell me, the fact that I have 2 blue-eyed parrots, that suggests that no, it's 90% likely that they came from population B. They could have come from population A, but there's only a 1 in 10 chance of that having happened. 9 out of 10 chances that they came from population B. And so this is very powerful to give you an idea of how good your hypothesis is. Not that it's simply the one that's left over after I've rejected other hypotheses, but it gives you an idea of how good your hypothesis is. All right, so that was kind of a simple-minded example of the application of Bayesian statistics. Let's dive into the deep end of the pool and the application of Bayesian approaches to phylogenetic inference. So, we're trying to evaluate the goodness, if you will, of a hypothesis. And we want the best hypothesis, given the data that we observe. In the case of phylogenetics, in reconstructing relationships among organisms, the tree itself is our hypothesis. And this is not a simple hypothesis, like did it come from population A or population B. A tree as a hypothesis is a function of lots of subsidiary hypotheses, including the topology, that is the interconnections between all of the OTUs, all of the species that you're studying, the length of the branches from one node to the next, or to the OTUs themselves, how long those branches are, the parameters of the DNA evolution model that you've chosen. So you've got numerous DNA models you could choose from, and the values of the parameters that you have for each of those. Those are all subsidiary hypotheses. And then if you choose to include it in your analysis, the gamma shape parameter to account for heterogeneity in substitution rates in different parts of the sequence that you're studying. And by the way, these methods are, although they can be shoehorned to use other sorts of data like morphological data, these are big tools in phylogenetics, at least, in use for analyzing molecular sequence data. Okay, so our tree is our hypothesis, and we want to find the best tree that we can. And what we're interested in, since we have the data at hand, we want to know what is the best hypothesis given the data that we have. And basically, we're looking for the posterior probability. That's our goal. We know that likelihoods can be calculated. That's straight. Might be tedious, but it's straightforward. That's what we were doing with maximum likelihood approaches to phylogenetic inference. So then we come down. We're going to ignore the probability of the data, since since we don't know that value and can't calculate it, because there's a huge number of possible hypotheses, and we can't evaluate the probability of the data for all of them. So we're going to be relying on the fact that the posterior probability is proportional to the prior times the likelihood. We won't know the absolute value, but we can compare posterior probabilities. They'll all be comparable. So we're left with having to figure out what the prior is. And So the prior is a hypothesis that you're coming to the analysis with, and you need to be able to specify what the probability of that hypothesis is, and that can be a real test. But typically, just like in the example with the parrots, when I said, well, we have no a priori reason to think that the sample came from population A or population B, therefore we'll just set them to be equal. That's often what people do in terms of phylogenetic analysis. That is that they posit what's called a flat prior. So they're basically saying that all trees, at this initial stage of total ignorance, all trees are equally probable. And well, there are other functions. There are other functions you can use to express priors, such as, once you get down into the gory details of, for example, the parameters of DNA evolution, you could stipulate a prior probability of the transition of an adenine to a thymine to be a normal curve, and then do that across all of your parameters. Just say, well, I don't know what the exact value is, but the probability is going to approximate, here's my hand, there we go, a normal curve, a bell-shaped curve. So what we're looking for is to find the tree. I shouldn't have said topology, because it's not only topology we're after. We're looking for the tree and all of its subsidiary hypotheses that has the maximum posterior probability. That's the quest that we have. The problem is, as I tried to illustrate in the last video, with telling you how many possible trees there are for a given set of OTUs, is that there are too often just far too many trees to evaluate. So we can't do this analysis in an explicit manner, that is, by looking at each and every tree and calculating its posterior probability. Not only is the number of ways of hooking those OTUs together astronomical, but we have all those subsidiary values that we can vary. Subsidiary hypotheses, the values of which we can vary. So we need an approximation technique. And what the software that implements Bayesian phylogenetics, well, not only phylogenetics, but a lot of Bayesian approaches to other questions in science, is to start with what's called a Markov chain Monte Carlo. Now, figuratively speaking, what we're talking about is, if you imagine let's say we took all the possible trees for a particular phylogenetic problem, and we imagine them in space somehow, and we reduce that space to, let's say, just 2 dimensions. Then we want to go through this parameter space where all the parameters of a tree are varied. So we have trees all over this landscape with different parameters, and each of these trees has a particular likelihood. And if it has a high likelihood, it's going to be a little hill in this parameter space. And if it's a low probability, it's going to be flat or maybe just a low hill. We're looking to find the mountains and climb up the mountains. The problem is that we're walking through this parameter space totally blind. We can assess where we are, but we can't see where the mountain is that we really want to climb. Of course, we're assuming that there's a mountain there, but that's the one we're after. So a Markov chain Monte Carlo simulation basically works something like this. So stick with that idea of a parameter space, a landscape that we're trying to find the high points in. So we start anywhere you want in that landscape and look at the tree there, and calculate its likelihood. I'm sorry, its posterior probability. What do I want? No, I want its likelihood. Sorry for the confusion there. We want its likelihood. So I start out, I know the likelihood of the place I'm at, the tree that I'm at. So now I want to randomly change some of the parameters that went into calculating that tree. It might be the branch lengths. It might be that A is closest to B, and now I'm going to change it to A is closest to C, or any of the parameters of the DNA evolution model. Change something. In the new tree that I calculate from after having changed those parameters, calculate its likelihood. Compare the new likelihood that I've come up with the likelihood I had in the position I started at. If the likelihood of my new tree is higher, that's my new tree. If the old tree was higher, then I stay where I am. And we're going to also, well, that's the next step. So in general, we're going to start at a place with a tree, change some parameters in that tree, recalculate it, get its likelihood. If the new tree has a higher likelihood, then move to that tree. If the old tree has a higher likelihood, then just stay where I was. And keep doing that over and over and over again. It's possible, though, that I might get stuck. You know, maybe the tree I started with has a, it's got a relatively high likelihood, and it's surrounded in my space, my landscape, by trees of lower probability. Therefore, if I just step off the top of this hill I'm at, they're all going to be at lower probability. I'm going to be stuck where I am. I can't get off of this little hillock that I started on to the mountain. I can't make it to the mountain, and that's what we want to do. So in order to accommodate that, we need another step. This is simply, before I go to that next step, this is the scenario that I was trying to describe in words there. Here they basically, it's not even two dimensions, it's a single dimension, where this axis here is the likelihood of a particular solution that you've come to, a particular phylogenetic tree. And it doesn't matter where we start. Let's say we're at this position. If I randomly change some of the parameters in the tree I'm at, and I come up with a tree of a higher likelihood, then I'm definitely going to move to that tree. And then I'm going to repeat that process here. And that's pretty steep. And so the R here is a ratio of the new likelihood to the old likelihood. And we're going to incorporate some kind of a threshold value, such that it's got to exceed the ratio, the difference between the two trees has to exceed a certain value for me to accept it. Up at the top here, I'm at a relatively high likelihood tree. If the new tree I calculate has a much lower likelihood value, then that ratio is going to be very small, and I'm unlikely to accept it. So I'm going to stay where I am. But here, the new tree I calculate is only a little worse in terms of likelihood than the one I was at. And so I might accept that. One of the rules of thumb is that you take this ratio and calculate it and say, okay, I have a 92% chance of staying where I was, but an 8% chance of moving to this new tree, as compared to this one where we have a big ratio difference, that it's what, 0.2 over 6.2. I have a 97. No, I'm not doing that math right, am I? I have I think that's a 0.3% chance of accepting it. It doesn't matter the absolute value. The point is that a very low probability of accepting that. Not zero, but very low. Whereas here, there's a decent chance that I might accept that move, meaning that I might step down in the probability in the hopes that in this case, this curve doesn't continue to go down, but maybe it rises once I get to that point and I start to hike my way up the mountain. So basically, this is the principle of Markov chain Monte Carlo simulation. One of the characteristics of a Markov chain simulation is that you have no memory of where you have been. So you can't go back to a place. You're just kind of stumbling forward in the dark, looking to find the highest place that you can. And once you get there, to stay. So ideally, what we're doing is randomly sampling from the distribution of those posterior probabilities for all of those trees. And focusing in on the likelihood, because posterior probability is going to be proportional to the likelihood. So higher likelihood, prior is the same, higher posterior. So the question that I posed a little bit before was, what if I get caught in a local maximum? Instead of being on the mountain, I'm on a small hill. The chance that I might accept a suboptimal step could get me out, but it needs a little bit more help, especially if our landscape is not gently rolling, but it's got high peaks and deep valleys in it. So the way that the algorithms do this is to take our MCMC, our Markov chain Monte Carlo simulation, and add another MC. So now we become a metropolis coupled Markov chain Monte Carlo, or some people call it MC cubed. So every one of these Monte Carlo runs that we're doing are often referred to as a chain. So one run is a chain. In a metropolis coupled Monte Carlo simulation here, you run multiple chains in parallel. The way I described the chain working before is what's referred to as a cold chain. And the metaphor will explain itself here in a second. But the other chains that I run are heated. Basically, the idea is, imagine that you're on a glacier. So instead of walking hills and mountains on solid ground, you're going through crevasses and hillocks and ice flows on a glacier. And in the heated chain, that glacier melts so that everything becomes a little bit leveler. You don't have the steep peaks there. You have more rounded hills. So you kind of flatten that likelihood landscape. And then you do the same thing in parallel with your cold chain. By flattening the landscape, by reducing the size of the peaks and the depth of the valleys, basically what you're doing is making moves more likely in your heated chain than they are in your cold chain. So you run a series of potential steps over and over again, assessing whether your likelihood is increased or decreased in the two chains in parallel. And then at regular points in your analysis, you flip them. You take the position in your heated chain and assign it to your cold chain, and vice versa, and then run them there. So regularly you're exchanging your heated and cold chains, basically allowing the little man on the hills that was walking on that graph to suddenly jump from one place to another, always looking and always he's keeping records along the way of where the highest point was, where the tree with the greatest likelihood and therefore the greatest posterior probability was. So that's, I've oversimplified in many ways the process here, but that's our point in of course like this. If we were going to be talking straight up systematic theory and analytical techniques, we'd go into much greater detail on this. But that's the basics of a Bayesian analysis. So each of those potential steps is a generation, and you run the analysis, basically trying to walk through your likelihood landscape for a large number of generations. And typically the number of generations is measured in the millions. I've seen analyses, 30 million, 50 million, 200 million steps. And at regular intervals along there, you're sampling the tree that your little man is at and recording the tree, all its parameters, and of course its likelihood value. All right. So then the question becomes, in a single run, I've got an idea of what my highest likelihood trees are. But then, have I gotten to the peak? If there's a peak in the landscape, have I gotten there? And the way you address this is by doing multiple runs, not only one cold chain and maybe a couple of heated chains, but the pair of those replicated. Then you ask, if I do 2 parallel runs, let's just limit it to 2, with cold and heated over here, cold and heated over here. I analyze for a while, look at the results, compare them across those two. Are the trees that both of these sets of chains have found, are the trees similar? And there's a statistic for measuring that similarity that's represented here on the y-axis. This is just the number of generations that you've run through here. Started out at 0 and they're up to up to 10,000 generations here. And so this is a comparison of the two chains, of the two cold chains. And are they similar or are they different? So up here, they're more similar, they're different, and they're a likelihood value here. You're comparing their likelihood values. I guess that's the way I should say it. And we see some variability because obviously there's a random element in here. We're hoping that it's a random element, because if it's not random, then your analysis is going to be invalid. And we see it varies a little bit here. But eventually, the metaphor people use is that this graph ends up looking something like a hairy caterpillar. I mean, it's not a straight line, but it's the slope of a line going through here is 0. At this point, you're saying these two chains have converged on a common solution, that they have found the best solution or the set of best solutions for your data, because they're not moving and suddenly jumping up. This one actually hasn't reached convergence, I would suggest, a little bit, because these set of values seem to be a little bit consistently higher than this set of values. But basically, you're looking for the point where all these things are flat. I'll also notice that here's where you start. And so once you start, you're not anywhere near your optimum yet. And so these values are low to begin with. People generally just ignore this part of the graph and just look at here where you have reached convergence, where you've plateaued out. This is called the burn-in, and people just ignore this level. How many values that is depends upon the analysis. Yeah, typically 10% or so of the total number of generations is just ignored. So you're up here, you've kind of stabilized, come to an equilibrium around a particular likelihood value. And you've got a set of trees that are in that area. They all may differ a little bit. They won't be exactly the same, but they're all pretty much the same. At least you hope. If they're not the same, then you won't have this plateauing effect. So once you decide that you're done, you take a consensus of those trees that have that highest likelihood. And so that's going to lead me to the next subject here, which is confidence in the trees that we have. And then I'll finish up by just pointing out some difficulties with Bayesian analyses. So when I said you take a consensus, I was talking about something very specific. You look at the trees you have and you generate what's called a consensus tree. So all methods, or all optimality criteria, let's put it that way, whether it be parsimony, maximum likelihood, or posterior probabilities, can produce trees that are, pretty much the same, but they vary here and there in little things. And so a tree with, might have one likelihood value and another tree has a slightly lower likelihood value. They're really pretty much the same, and so we want to consider those. We don't want to just throw that away because the difference between them is probably insignificant. A consensus tree is a tree that presents the information that is shared amongst multiple possible trees. So there are different flavors of consensus trees. I'm just going to talk about two of them: a strict consensus tree and a majority rule consensus tree. Here's the definitions, but let me show you what I'm talking about in terms of strict versus majority rule consensus trees. So up at the top here, we have three trees that we'd have arrived at from our analysis, classifying or grouping together the species A through F, and they're all in the same order here. So tree 1, A, B, and C are all, well, first of all, it splits our 6 OTUs into 2 groups. A, B, and C belong in one group, and either I don't have data or the data are ambiguous as to which pair is most closely related to each other. In the other group, I do have data that E and F are more closely related to each other than they are to D. So that's my first tree. The second tree is fully resolved. It's telling me, yeah, I've got those 2 groups of 3, same 3, A, B, C on one side, D, E, F on the other side. But on the one side, A and B are closest, and then C. And on the other side, E and F are closest, and then D. Then my final tree has the 2 halves, AB, ABC on one side, EDF on the other side, just like tree 1. I can't tell, either I don't have data or the data are ambiguous about which is best here. But on this side, it's saying it's DF that are most closely related, and E that is not. That is the outlier there. So you can see that these are, this tree and this tree contradict one another, in that they're positing, this one is saying that E and F are most closely related. This one is saying D and F are most closely related. And let's see, tree 2 is consistent with tree 1. It contradicts tree 3. But they have pieces of information that are in common. And so a strict consensus tree is a tree that seeks to display to you the pieces of information that are found in all of the trees that you're looking at. So in this case, the only thing that all 3 of these trees have in common is that they split our OTUs into 2 groups of 3, A, B, C, and D, E, F. And that's exactly what it does here, A, B, C, and D, E, F. So that's a strict consensus tree. Any grouping that it's showing you is found in all of the trees that went into its calculation. Majority rule consensus tree, on the other hand, is a little bit looser. Allows for that you don't have to have unanimity in the vote that's taken. Majority rules. So these are the same input trees that we had before. So let's see. We have ABC. Well, first of all, split into 2 groups: ABC, DEF, ABC, DEF, ABC, DEF, and that is reflected in the majority rule consensus tree. So a strict consensus tree is kind of like a subset of majority rule consensus tree. On the ABC side, we have an unresolved trichotomy here, an unresolved trichotomy here. Here we have resolved the trichotomy, but nobody else is saying A and B. These guys don't know, and then C on the outside. So what on this side of the tree, basically the unresolved trichotomy wins. On this side, on the DEF side of the tree, we have tree 1 saying E and F are most closely related. Tree 2 says E and F are most closely related. Tree 3, however, says D and F are most closely related. 2 out of 3 say E and F, majority wins, E and F shows up in the tree. So basically, for a Bayesian tree, a Bayesian analysis, sorry, you're going to have literally hundreds, if not thousands, of trees. You could get a strict consensus of all those trees, and you'll likely end up with a total polytomy with nothing that is shared amongst all of those trees. And so people typically go for a majority rule consensus tree. You could change this. This could be 50%. You could put it at 70%, whatever value you're comfortable with, where you're still getting some information. I mean, the higher the value you place, then the higher percentage of trees have to have that value. So you're getting more and more conservative. You're looking for the real core of what is shared amongst those all of those trees. I have never seen anybody go lower than 50%, because then it seems like you're just flipping a coin at that point. So that's what you do with a Bayesian tree. Let's move on. You'll also see, if you're looking at the results of a Bayesian analysis, so you see the tree that the authors produce, and then they'll put numbers on those trees. And the numbers in a Bayesian analysis represent the posterior probabilities of what they call bipartitions, or the groupings, or the clades in that tree. That is basically how often are these groupings, what is the posterior probability of finding these groupings in the tree. And because they're posterior probabilities, these are probabilities that the group that they're representing is true, is a real result, given the data at hand. You're searching for a posterior probability of 100%. That is, all of the trees have this group at hand. And therefore, your hypothesis that that group exists is true. Lower values, just like there's no absolute cutoff in an alpha value in frequentist statistics, the value at which you ascribe significance to your result and reject your null hypothesis, there's nothing magic about the posterior probabilities of a Bayesian analysis. Although typically people are looking for something at 90% or higher as a posterior probability. What about the other analyses? And I guess I'm going to focus here on maximum likelihood trees. Now, there are similar confidence measures. Parsimony analyses will also use bootstrapping, which I'll describe in just a second here. They have some other statistics that are used, but generally when you're analyzing molecular data, parsimony analyses come out either clearly wrong or totally ambiguous, almost totally ambiguous. So let's just limit ourselves to the maximum likelihood trees. There are a couple of ways that people assess the confidence that they have in the tree that they get as a result of a maximum likelihood analysis. The most common is a method called bootstrapping. And this name derives from the idea, I guess, of pulling yourself up by your own bootstraps. I mean, taking care of yourself, looking to yourself for support and motivation. That's the psychological point of view. What does it mean here in terms of analyzing maximum likelihood trees? Basically, in a bootstrapping analysis, so we've already done our maximum likelihood analysis on the total data set. To do a bootstrap analysis, you take your original data matrix. So you got all your sequences and all your OTUs. And so that's your starting data matrix. And now you're going to create a new data matrix that is derived from the original one by a process called resampling with replacement. That is, you're going to have the same OTUs in the list, but you're going to construct your new data matrix with a new set of molecular data. You're basically going to go in to the original data matrix at random, pick a column, copy it over to your new data matrix. But then once you pick that column, you're not eliminating that from the original data matrix, you're replacing it. And then once you've done that once, get one column, you go pick another column at random. Put it in your new data matrix, but don't eliminate it from your original data matrix. Keep doing that over and over until you have a new data matrix of the same dimensions as your original data matrix. Now what this means, unless in the very unlikely case in which you, in a random process, only selected every column once so that your new data matrix exactly replicates your original data matrix. What it means is that some of the data from your original data matrix is not present in your new data matrix. And some of the data is represented more than once. Okay, now with this new data matrix, do your maximum likelihood analysis again. Save your result of the maximum likelihood tree. Okay, do it again, and again, and again, hundreds, or more likely thousands of times. And then compare all of those trees from those 1,000 bootstrap replicate analyses you have done. Look at the trees and look at the bifurcations. Look for the groups. By bifurcation, I mean you have a branch that comes up and splits. Who's on the end of those two that split, the two branches of that split? And report the percentage of cases in which a particular group occurs on all of these trees of the bootstrap replicates. Again, the ideal number is going to be 100%, that the group is represented in all of the trees that come out of these analyses after you do these bootstrap replicates. And that is known as a bootstrap support value. And so in a maximum likelihood tree, if you see numbers at a node or along an internal branch of the tree, that is going to represent the bootstrap value. So if you see a value of, I don't know, let's say 70%, that means in my 1,000 analyses that I did, bootstrap replicates, 70% of the time that particular grouping occurred. So what's a good value? Well, obviously 100% is best. Once you get below 50%, you're kind of flipping a coin. And again, there's no magic value of what's significant in between. It's giving you an idea of how well the data you have support the hypothesis represented by that tree. A similar way of doing these sorts of confidence analyses is something called jackknifing, which is basically doing the same thing but resampling without replacement. So you're ending up with a smaller data matrix there. Conceptually, of course, you could also do it with the OTUs, but in practical purposes, the OTUs are set. What you're interested in is how well did the sequence data support the analyses that I end up with. So in Mega, bootstrapping analyses are implemented under the once you start to create a tree, you'll see I think it's called a test of hypothesis or something like that. And in there you can select to do a bootstrap analysis, and you can specify the number of bootstrap replicates you want. You can vary those. One final caveat here is that the bootstrap analysis is not an independent test of the results that you've gotten from your original analysis, because you're using the same data. What it's telling you is it's not the probability that your tree is true. It's really telling you how well the data you have support a particular hypothesis. Whereas in a posterior probability, you are saying how good the hypothesis is based upon the data that you have. So let's wrap up here before we get to a summary of just some issues that arise with Bayesian analysis. Bayesian analyses started to be possible, that is, in a time frame of a human lifetime, in the early 2000s, and they still are very intensive, computationally intensive analyses. But they've become very popular because of the ability to directly assess how good a hypothesis is. So that's very intellectually stimulating, appealing. But they do have their issues. One is that posterior probabilities emerging from a Bayesian analysis for particular clades. So you do analysis, maximum likelihood, you do it in Bayesian. The posterior probability values seem to come out consistently higher than the bootstrap support values in the maximum likelihood analysis. Some people have interpreted this as the bootstrap values being more conservative, so you can place greater confidence in them. Other people fear that it leads to misplaced confidence in Bayesian analyses. When you see that 100% there, you say, oh, that this hypothesis is true. I have found the truth. So that's viewed with some concern. I've talked about the interpretation of posteriors or bootstraps a little bit, that a bootstrap value is telling you how well the data support this hypothesis. It doesn't tell you directly how good the hypothesis is. One of the real sticking points for many people, and I guess I count myself here, is the requirement in a Bayesian analysis that you must assert what the prior probabilities of the hypotheses are. You have to know this in advance, and you run the risk. Every manual for the softwares that implement Bayesian analyses will tell you that if your prior probabilities are inappropriate, you're going to get garbage results, garbage in, garbage out. Or maybe a more kind way to say it is that if you have selected your prior probabilities in a very subjective manner, then that's going to influence what your posteriors are, and they're going to be subjective as well. So it's not as cut and dried as we might hope or expect a scientific analytical technique to be. Certainly, you can strive and do tests and adjust your priors such that they are more realistic and are testing interesting hypotheses. And this is an area of development in the people who write the software to implement Bayesian approaches, to have more complicated models than the very simple models that the earliest algorithms implemented simply for computational purposes. So one solution that you'll find very often in the literature is that rather than the authors saying, well, I like maximum likelihood for these reasons, therefore I'm going to eschew doing Bayesian, or conversely, I believe in Bayesian, maximum likelihood only gets me halfway to where I want to be, so I'm only going to do Bayesian. I mean, you could do that and defend your position. You might run into issues with reviewers, but I don't think that's a real biggie. But in order to avoid such things, they'll do both analyses and then look for commonalities between the results that you find. I have a colleague who his position is that if the data that you have at hand have a clear phylogenetic signal, that is, that the pattern of relationships amongst your OTUs is in those data, and it's up to you to extract them, then if it's a strong signal, then both a Bayesian analysis and a maximum likelihood analysis, and maybe if you're lucky, even a parsimony analysis, will reflect that phylogenetic signal. So then you look for the common elements among those ways of approaching the work. Here, practical issues tend to come in, and that Bayesian analyses tend to be much longer. I mean, some Bayesian analyses are the time to run is measured in months, even on supercomputers. So these are not trivial exercises in large analyses. So doing both Bayesian and maximum likelihood is often impractical. Maximum likelihood is much better under those circumstances simply because it can be done. I'm skipping over one approach here that I think is probably more relevant to a systematics course than what I'm trying to describe here, the basic techniques. But let me just mention it very quickly. What I've been describing is the analysis of a gene sequence for a set of OTUs. In your phylogenetic project, you've got what, 3, maybe more genes for your set of OTUs. And one way to analyze these is what's called a supermatrix approach. That is to put all your data together, each sequence, and just say, have sequence 1, at the end of that I'm going to attach sequence 2, at the end of that I'm going to attach sequence 3, analyze them all separately. That has positive and negative aspects to it. A different approach is to analyze each of your sequence separately and come up with a gene tree for each sequence, and then coalesce your gene trees to find how they best agree. So these are two different approaches. The supermatrix approach is more well developed, more widely used, but the alternate gene tree coalescence approach has also its own validity. And again, if you have a strong phylogenetic signal, you would hope you would be getting the same answer. And so this is a way to see, perhaps find the sections of the data, the partitions of the data, the sequences that are generating the noise in your phylogenetic signal. But as I say, that's a topic that's getting over our heads for our purposes for this course. I wanted to make you aware of some of the available software packages that you can use. Of course, there are R libraries for many of these things these days, but there are lots of dozens and dozens and dozens of independent software packages to do parsimony analyses, maximum likelihood analyses, Bayesian analyses, even other maximum compatibility, lots of other ways of analyzing the data. Here's just a few that you'll probably run across in the literature. It's not the whole list because these things are sprouting like weeds in my garden these days, but Joe Felsenstein, remember I talked about him with long branch attraction, for many years has been trying to keep track of the software packages that have been developed. The listing he has on his website there is probably a little bit out of date, but it will certainly get you started and certainly give you an idea of the number of different possibilities that are out there. But as you're reading through the literature, you'll probably run across some of these names of analysis packages, so I thought I'd just introduce them here. The first one is called POP, which is an acronym that stands for Phylogenetic Analysis Using Parsimony. It started out as a parsimony program, but it's now basically a maximum likelihood program. This is a program developed by Dave Swafford. It's a real classic. It's a little bit out of date, a little bit out of vogue now. There are new packages that can handle the massive amounts of molecular data that we can generate these days in a better way. But it's still out there. I should say that many of these, not all, POP, I'm not sure what the current situation is with POP, but you used to have to purchase a license to use it. Many of the rest of them, however, are free of charge. For maximum likelihood analysis, a very common package that you see people use. I mean, a lot of people use Mega in the literature, don't get me wrong. But RaxML is one that's very commonly used. This is developed by Alex Stamatakis from Greece. RaxML stands for Random Accelerated Maximum Likelihood. He has a similar program that is for really big data sets, which he calls XML, for exascale maximum likelihood. So for the next video, when we start talking about phylogenomic analyses, you'll see some people, you can use RAXML, but XML will often work better. One of the leading programs for Bayesian analyses was developed by John Hulsbeck and Fred Ronquist. Fred Ronquist is an entomologist. He's a specialist on gall wasps. And that program is called Mr. Bayes. It is also free for download. Although Mr. Bayes is capable of running on a laptop, the calculations are intensive enough, especially if you're doing multiple chains in parallel, that this is really something more appropriate for a dedicated workstation or supercomputer with multiple cores and lots of memory to use. There are just a slew of other Bayesian programs, Bayes phylogenies, BEAST, the list goes on and on. You can see lots of them listed at Felsenstein's website, and they continue to be developed. It's like a new flavor every year. So all of these are still under rapid development, and as I say, there are libraries for most, if not all, of these approaches as well. So how would I summarize all of this hour and 15 minutes that I've been rambling on here? I wanted to contrast the more classical frequentist sorts of approaches to science, really, with Bayesian approaches, where in the context of phylogenetics, we're talking about likelihoods, a frequentist approach. So we're looking at the probability of the observed data given the hypothesis. So we're looking at the probability of getting these data if our hypothesis is true. Whereas a Bayesian approach takes looks at it the other way around, saying what is the probability of my hypothesis given the data that I observe. So it's very attractive, and that gives you a direct assessment of how good your hypothesis is. The posterior probabilities, which are the measuring stick of your hypothesis, these are proportional to the product of the prior, which you have to specify in advance, and the likelihood, which is calculated from the data at hand against the hypothesis. Can I get it all? The metropolis coupled Markov, I can't believe I can't remember, the MC cube, metropolis coupled Markov chain Monte Carlo process. Because we can't get those posterior distributions for all trees, this is a mechanism to, if it's appropriately designed, and hopefully to randomly sample from that posterior distribution to find the best trees, the highest mountains in that particular likelihood landscape that you have. And then we have different methods of measuring confidence in our result. Either consensus trees, bootstrap probabilities, not probabilities, bootstrap percentages, or posterior probabilities, all of which need to be taken with a grain of salt. There's nothing objective about a particular number for bootstraps or posterior probabilities that says, here's where significance lies. This is a value that's going to depend upon your own approach to the data, how your interpretation of the data, and how much weight you should place on it. Obviously, very low values you're going to probably ignore. Very high values you're going to stress, but those values in the middle, there's plenty of room there for variation in interpretation. So I'm going to leave it off here. And next time we're going to jump into some of the latest analytical techniques, working not with 1, 2, or 3 genes as you are in Mega, but with literally thousands of genes at the same time, looking at phylogenomics. So until then, take care and stay well.